All right, welcome everyone to the November SJAA Imaging SIG. Tonight we have a treat. We have Akarsh Simha, who's going to tell us about a project of his, useful to visual observers, but taken from technology related to us imagers. And just I'll say a few sentences about Akarsh. I met Akarsh because he is a contributor to K-Stars. In fact, for 1 year, he ran the K-Stars project right before the current maintainer, Jassim Mutlaq, started. Akarsh is responsible for the fact that K-Stars can render 100 million stars and not fall apart, but and do that efficiently. I got a PhD in physics from UT, University of Texas, and currently works as a software engineer in the Bay Area. So without further ado, take it away, Akarsh.
Thank you, Hi. Hi, everyone. I'm sort of an outsider here because I think those of you who follow TAC or elsewhere know that I'm a visual observer. I have dabbled in imaging, but I'm sort of, it's not as exciting to me as visual observing. And I don't have the equipment to take good images. I have done a little bit of astrophotography, so I know how to, stack and, to some degree, minimal processing and so on. So, but I'm almost entirely an eye at the eyepiece person. But where this all started, let me just share my presentation so you're not looking at the screen. Where this all started is, I think 7 or 8 years ago, even before I guess the Celestron had a product out or anything, one of my friends who was an imager, he said, look, we're using plate solving heavily to point our telescopes. You should just be doing that with your visual scopes. And I never thought about it seriously enough until the pandemic hit and I had some spare time on my hands and so on. So I started saying, you know what, I have nothing else to do. Let me try and build this system. So this is essentially my pandemic project. And it's still very prototype-ish, but I'm going to mostly focus on the technical ideas that went into this project. So the idea here in a sentence is to try and use plate solving to point visual Dobsonian telescopes. So why do I need to do something this complicated? Well, clear, dark weekend nights are precious, and you need everything for visual astronomy to work out. And there's the question of what do you enjoy? Do you enjoy finding objects? Do you enjoy observing them? Or do you enjoy both? For some people, there is a lot of joy in finding objects, and I am not one of them. I mostly enjoy observing objects. So why not automate the finding, right? Star hopping to me is a chore, and the less I need to star hop, if I have a machine star hop for me, I will be much happier. And in some sense, what plate solving is giving me is a way of centering the field that I want without me looking through the finder scope and trying to figure out star patterns, but instead have the algorithms take care of that for me, right? So that's my motivation. So if you look at how most visual observers point their telescopes, they are either doing manual star hopping, or they're using encoders. Encoders, are also known as digital setting circles. Basically, they're these tiny devices that use optics to be able to tell how much a shaft has rotated, right? And so if you mount one of these encoders on your altitude and zero it correctly, as you move your telescope in altitude, you'll be able, it's going to register how much you moved your telescope. You probably know about encoders because they're inside your mounts, your imaging mounts, and that's how your mount knows where it is. But in the visual observing land, it's something that people retrofit on telescopes. When I bought this telescope, it had no encoders on it. And for many years, I thought I wanted to put encoders on it, but I didn't have the mechanical skills to do it. You need to make a specific kind of shaft, and and after you do all of this and mount encoders on your telescope, you get okay pointing. You might hit an object within 15 to 20 arc minutes if you're lucky. At least this is my impression. I've not heavily used encoder systems. The one time I use them, it doesn't hit you right at the center. And if you want it to hit really accurately, you have to have your telescope leveled, and you need to build a pointing model so that it points correctly. I think this is a problem with imaging mounts as well, in some sense. So the advantage with plate solving is, in principle, you don't need to retrofit anything. It's just replacing your eye at the finder scope or at the eyepiece with a camera, right? And in my prototype, I think I get great accuracy. Unfortunately, the demo that I recorded has problems. I think I know what the problems are. The accuracy there is not good. But in general, I've gotten something like 5 arc minutes to 10 arc minutes pointing, and I believe it can be improved down to even more. And the ease of use is pretty good. And in my prototype, it's not very robust, right? But I believe that if we take this idea and run with it for many years with many people trying out different things, we should be able to get a product that, or a concept or whatever, that beats encoders at what they do, which is some sort of a electronic finder scope that I can just mount on the top of a Dobsonian or like a visual telescope, and suddenly it gives me push to capabilities, right? Without having to mount these encoders and build pointing models and so on and so forth. So my dissatisfaction with encoders mostly comes from the fact that I'm usually observing arc galaxies or Hickson groups and such things. And these things are tiny and very faint. And when you center one of these arc galaxies in an 18-inch telescope, which is what I have, when you put your eye at the eyepiece, you usually see nothing. And you need to wait for your eye to adapt to the field and gather enough signal or whatever to start seeing things. So if my pointing is 5 to 6 arc minutes off, I still have to do a little bit of star hopping in the eyepiece, because to find out where exactly this object is. Ideally, I would like it to be in the center of my eyepiece when the system tells me that it is. And encoders are definitely not able to achieve this without a pointing model. And I think my prototype is also not able to achieve it, but I have hope that with some more engineering, it'll get there. So that's the context for why I'm doing this. So like I said, the dream I have is that there probably exists an electronic finder scope that somebody will build, and you replace the existing finder scope on your telescope, with this electronic finder scope, and you suddenly have push-to capabilities. Your system should be able to tell you how to push your telescope to get to the object and where it's pointing. The futuristic dream here is that it'll communicate over wireless with your laptop or tablet or phone or whatever. So you just mount this thing and you're good to go. You might know that Celestron actually has a product, but I believe that the visual version of that product is not as accurate as I would like it to be, and it uses the phone to plate solve, which I've never used it, so I'm not very sure of how exactly it works. But yeah, so I think this group probably doesn't need to see this slide at all. You probably know what plate solving is, but in case there's somebody in the audience that doesn't, it's essentially both it's this concept that was introduced in this paper astrometry.net by Dustin Lang and others. Basically, it's this idea that given a photograph of any region of the sky, you should be able to tell me, give me a mapping from every pixel on that photograph to the array deck coordinates corresponding to that pixel. So and they just didn't propose this idea or an algorithm, they actually implemented it. And so they have open source software that can find the location, orientation, and scale of any picture of the sky. So once you have the location, orientation, and scale, you can map every pixel position to an array deck pair of coordinates. Out of curiosity, the paper is out there. It does so by matching star patterns, triangles, and quadrilaterals, and it compares them against the database. You can download the software. You can also try it online by uploading an image. And you amateur astrophotographers are already using it heavily. Visual observers are not. So that's what I hope to change with this prototype. The other great thing about plate solving is it's never seen a false positive. It might say, I don't know what to do with this field and bail out. But if it says that this field is so-and-so, it's almost certainly right. And I've seen it jitter around, but not by much, right? So maybe like two arc minutes is how much jitter I've seen at most. And that's probably because of smudging of stars and things like that, and lens modeling and whatever. So I have a demo here. I think I will skip this because most of you are familiar. And if somebody wants to see it, I'll bring it back. So what's the system I'm trying to build in conception? So this is not my implementation, but ideas on how we might bring plate solving to visual astronomy. Just to go back, keep in mind that every one of these visual telescopes has a finder scope that's on it. I guess you can't see my finder scope; it's not mounted up there. But you've seen what a telescope with a finder scope is like. You know, people have a telrad and a finder scope and such things. And the idea here, all through, is that I'm trying to replace that finder scope with something electronic. Let's first talk about plate solving assisted go-to as used by you folks, imagers, right? You have the ability and the stability of tracking to put your camera in your main prime focus or whatever and take pictures through your telescope. So if you are working in that paradigm, you have go-to, you have great tracking, you have a stable mount, then what you can do is very simple. You take a picture, you plate solve it, and you find the plate coordinates, the plate center coordinates. You have some target in mind, let's say Orion Nebula or whatever. You know its RA index from a catalog. You find the error in the RA index, and if the error is larger than your tolerance, then that means you're not on the object. So then you correct the scope position. So this way, you don't need to build a pointing model. If your scope's go-to doesn't hit, you can just use plate solving to fix it. And I believe K-Stars and ECOS already does this as part of its routine go-to correction system. And of course, if the error is within your tolerance, which might be a few arc minutes or even less, you're done. You're on the object and you have stable tracking, so it keeps tracking. Now, if the main telescope is a visual telescope like mine, this is my telescope here, and you can see as I wiggle it that its mount is anything but stable. These Dobsonians, if you try to do imaging with them, at best you're doing lucky imaging. Well, I have tried to put planetary camera on this and do some lucky imaging, and it is a nightmare. I mean, I might shoot 100 frames and have 3 good frames, right? So that's how unstable these mounts are. The sort of quality of tracking used in visual astronomy, I track this with an equatorial platform. My platform is actually designed for 30 degrees north latitude. So actually I have 8 degrees of polar alignment difference, and I still use it. It works well enough for visual, basically, taking images through the main telescope is a nightmare. Plus, you also know that plate solving smaller fields is much harder because there are just so many smaller fields in the sky that you have to search through. Your search space is much larger. So plate solving wide field images is much faster. And the focal length on an 18-inch telescope like this is 2000 millimeters is my focal length. So if I put a typical camera there, I'm going to have a 13 arcminute or a 6 arcminute field, depending on whether I have a Barlow or not. And so it's going to take forever to solve those tiny fields as well. So that's why the idea that I'm proposing is to plate solve through a finderscope. And this means that just like you as a visual observer would align your finderscope, like center Jupiter or some bright object or bright star in your main telescope, and align the finderscope so that it's, so you need to also align the finderscope even if it has a camera in it, right? The best part is that this alignment you don't actually need to optically align the finderscope with the main telescope. So one of the main ideas here is that if you figure out what is the degree of misalignment between your finderscope and your main telescope, you just memorize that misalignment and apply that every time you're done. You don't actually need to physically and optically align the finderscope. So I have a 1-star alignment process, which works as follows. I center a known star in the main telescope, and then I plate solve through the finderscope. The plate solving algorithm tells me, here's the center coordinates of my plate. This is the RA deck. But I know which star I have centered, so I know the actual RA deck in my main telescope. So I just ask I just compute with the plate solution that I have found, what is the pixel offset on the plate X, Y, corresponding to the star that is centered in the telescope. So here's a graphic that that explains this. So the optic axis of the finderscope is pointing somewhere. It's not aligned with the main telescope. That's the center of this plate. The actual star that I've aligned in the finderscope is at some offset X, Y, and my 1-star alignment procedure essentially memorized that offset. So if you're working with digital setting circles, which is another word for encoders, you actually need to align 2 stars or 3 stars. So even the alignment process here is simpler. You just need to align 1 star. Okay, yeah, and like I said, no need to optically align the finderscope in the main telescope. If this confuses you, think of it this way, that if you think about the telescope axis and finderscope axis as vectors, then the difference in those 2 vectors, which is the offset, that rotates rigidly with your telescope system, assuming that there's no flexure in your telescope system and so on. Assuming that everything rotates rigidly, this offset is going to remain fixed no matter where you point the telescope, right? So that's why just knowing this offset is good enough. Okay, so how does plate solving work if you're trying to position a visual telescope by plate solving through the finderscope? So by the way, just to give you context, my finderscope is 270 millimeters in focal length. And with my ZWO ASI 290 MC camera, which is overkill for this purpose, but this is the camera I had, I get a field of view of about 1.5 degrees. So that's how wide my field is. And if I'm not tracking properly for a few seconds, it really doesn't matter for what I'm doing here. So that's just to set up how the finderscope addresses the problems that I mentioned with plate solving through the actual main telescope. So anyway, so how does plate solving through a finderscope work? It's very similar to the previous flowchart I showed. You take a picture through the finderscope now, you plate solve it, and you compute the RA deck coordinates corresponding to the plate coordinates that you memorized X, Y during the alignment process. You don't look up the center coordinates, instead you look at the offset coordinates. And then you ask, how different is that from the target RA deck? You get a offset in RA and an offset in deck. And if we are not within tolerance, then we correct the scope position. This is now assuming that you have a go-to. I guess this is similar if you would like to conceive of something. It's like the Celestron product that is meant for Celestron mounts. I don't know what it's called. I think it's one of the incarnations of their star sense system, which is a small finder scope that sits on top of your telescope and guides your celestron mount. So it's sort of like that. And you have to do a 1-star alignment even there to compute this offset. I did not look at Celestron system to do this, by the way. I've still not studied Celestron system. Okay, so now visual astronomers have even more problems than this. We don't have go-to, a lot of us. So I track my telescope on an equatorial platform. And if you don't know what an equatorial platform is, it's a very crude device that it's a platform for your telescope that tracks the telescope for maybe an hour along one axis. And it does so by rocking the telescope around the pole. And maybe you'll get an hour of tracking and then you reset it. So it's a tool that's used by a lot of visual observers to get tracking on their scopes. So I don't have go-to, I have to push my telescope. Okay, so how do we adapt plate solving to push to? This is surprisingly a lot more complicated than you would imagine that it is. So in fact, we don't even really need to, we don't need go-to or even tracking in principle. I still need tracking for my setup, and I don't think that's I think that's a software limitation and not an actual limitation. But yeah, the sky drifts 1 arcminute in 4 seconds. And if the positioning accuracy that I care about is 1 arcminute and my exposures are under 4 seconds, I don't even need tracking in principle, right? But in practice, I do need tracking because the plate solving algorithm doesn't like smudged stars in my prototype. But I believe that can be solved. And the limiting factor in error that I encounter seems to be flexure, because I get much more than 1 arcminute. My exposures are 2 seconds and I get much more than an arcminute of error. So my limiting factor is almost certainly flexure and other things with this big tube not acting like a rigid body, right? So that's not the problem. You don't need go-to, you don't need tracking to do the plate solving part. The problem is that plate solving takes time. And the best I've managed with the entire stack so far is 1 solve per 3 seconds. That's about maybe a second and a half for the exposure, about half a second to transfer the data from the camera to my laptop, and about half a second to solve it. So the solving itself is extremely fast because I know its scale hint. During the alignment process, I actually figure out what is the scale arc second per pixel of my camera. And once I give the solver the scale, it's not doing a blind solve, and that's extremely fast. So I can get a solve every 3 seconds or so. But for pushing a telescope, we need extremely fast feedback. We want, 10 frames per second at least, right? So you know how you're moving. Of course, if it's a motor and you say, oh, you're 15 degrees off, the encoders in the motor itself know what 15 degrees is. So you can run the scope 15 degrees, but I have no sense for what 15 degrees is. So I want to be seeing some feedback saying I'm getting closer to my target or not. And so I need faster feedback. And plate solving, I mean, even if I bring down the exposure, bring down the processing, I don't know if I will actually get to the point where I can solve fast enough that I can just push my telescope with plate solving. So the solution I've come up with, and I suspect that Celestron does something very similar, is to combine plate solving with something else that gives me fast feedback. And that is encoders or IMUs. And I'll explain what an IMU is. Now, I started this entire thing with the premise of avoiding encoders, right? And saying why I don't like encoders. There might still be advantages to adding plate solving to a telescope that already has encoders, because you could bring the accuracy, you could increase the accuracy, and also avoid doing this 2-star alignment because plate solving tells you where you are. So, it has advantages, but I wanted to avoid encoders. So I went the IMU route. And what is an IMU? IMU stands for inertial motion units. These MEMS devices, microelectron mechanical devices, these days they're everywhere. They're in your phones, they're in your cars. They're just pretty ubiquitous now. And what they are is a 3-axis accelerometer, 3-axis gyroscope, and a 3-axis magnetometer, X, Y, and Z, basically 3 axes, all combined into a chip. And if you are a tinkerer who works with Arduinos, you can just buy this Arduino 9-axis IMU shield, which is what I use. And it can give you approximate orientation. Now, what these sensors are good at is they can sense changes in motion. They are very noisy. They are very inaccurate. And people who have tried to use them to point their telescopes, there are threads on TSC and so on, they just don't really work very well. Maybe you'll get a degree or 2 degrees. You'll be a degree or 2 degrees off, which is a complete deal breaker. So yeah, these devices are fast, they are cheap, they are small, but they only provide rough positioning. So that's the problem with them. But hey, they are fast. So that's good enough for me. I can combine it with plate solving and get something that is accurate and fast, because the fast comes from the IMUs and the accurate comes from the plate solving, right? So that's what I'm trying to do here. Yeah, so I already mentioned that combine plate solving, which is slow but accurate positioning, with IMU output, which is fast but rough positioning, right? But the caveat is now there are more things to align. The IMU has an X, Y, and Z axis that is printed on the circuit board, if you like, depending on how the chip is oriented. And now I have a problem. I have to figure out how to align this IMU with my telescope axis. So in some sense, there are 3 axes now, if you like. There's the telescope axis, not shown here. I've just marked an arrow. There's the finder scope axis, and then you can conceive of an IMU axis, even though really we should be talking about frames and not axes, but yeah. I don't want to have the user try and align this IMU to arc-minute accuracy with the finder scope axis. That's a deal breaker, right? So I must assume that the IMU is arbitrarily oriented with the telescope. Okay, so there is that. So I need to find a transformation between the frame of the telescope, or if you like, the horizon north, and the frame of the Earth or the observer, and the IMU frame. And there is, sorry, I meant the telescope frame and the IMU frame. So I need to find a transformation between those two. And the other problem with these sensors is that magnetic north is unreliable, because they're going to use a magnetometer to find which way is north. And that sort of is affected by all sorts of things. Even if I have a metal object next to my telescope, or next to the IMU, if that metal happens to be iron and has a little bit of stray magnetic field, that can throw off its sense of north, right? And this is a problem that's very challenging to solve. And the way I solve it is to assume that the north is unreliable. So I only think of, I only use the IMU with an arbitrary azimuth offset. So that means I need to do 2 pieces of calibration. One, I need to figure out how my IMU is mounted on the telescope. And the second is I need to figure out which way is north, because the IMU is north is unreliable. Well, the great news is this does not add more manual alignment steps, because we can use plate solving to keep calibrating these sensors, like I mentioned. So the algorithm there that I'm using is pretty involved, so I won't get into the details. I'm just going to show a caricature of it in the coming slides. Yeah, like I said, lots of complicated math, but it's working. So now, let me explain how I do the calibration. So there are 2 things to calibrate, which means I need 2 data points to calibrate the IMU axis to the finder scope axis. So the first data point comes for free along with this 1-star alignment that I have to do between the telescope and the finderscope axis. So the alignment procedure is as follows. I center a known star. I capture and solve through the finderscope. I compute this pixel offset x, y based on the alignment stars array and deck. And that gives me one calibration point for it. It also gives me one calibration point for the IMU because I read the IMU at the same time. I know from my geographic location and time what is the altas of my telescope because I know its array and deck. And that gives me one calibration point for the IMU. That tells me one piece of information amongst these two calibration informations that I need. The second thing, the second alignment step is very simple. I just need to move the telescope, just literally move the telescope, right? And once I move the telescope, it triggers, I have plate solving usually running in a loop, so it triggers a capture and solve, and it computes the altas of my telescope, and I know what the IMU reading is. So I have the second calibration point just by moving my telescope. So the first calibration point tells me how the IMU is rotated with respect to the telescope axis. The second calibration point tells me which way is north in the IMU's frame of reference. And from these two calibration points, I have a full way to map the IMU's output to the positioning of my telescope. Now, the thing is, this is unreliable. And I know this because these sensors drift over time. They have noise, they have all sorts of problems. And the stray magnetic field can come and go and so on. So this calibration keeps running in a loop. Every time I have a plate solve, I have new calibration data point and I can add it and recalibrate the IMU. So this keeps happening. And every time I move the scope by a significant amount such that I can figure out north, I compute the new north and again, recalibrate that. So both of these calibration steps are repeated every time they are possible. Okay, so that's the calibration and alignment. How do I use this system? So the way it works is capture and solve runs in a loop. And again, we pick up the array and deck of the scope position, which we know from the pixel offset, and we calibrate the IMU in the process. This is, I've gone over this a bunch of times. And I'll come back to this pause image part in a moment. But now, what I do is, because I have just recalibrated the IMU freshly at every plate solve, I'm able to use trust the IMU over short movements or short periods of time, and use the IMU to give guiding instructions in altitude and azimuth. How do I move my telescope? Basically pushing instructions to the user at 10 frames per second, which was the initial proposal that I had, right? And so now we have a servo in some sense where the user moves the telescope. The user is the actuator of the servo system, and the IMU is what's reading the position of the telescope and giving the user the error signal, right? So we have a fast servo that involves the IMU, and we have a slow servo because every time the scope is stationary, I'm able to take an exposure, make a plate solve, and recalibrate the IMU and present a new offset to the user. So there's a slow but accurate servo, and there's a fast but inaccurate servo, and the two work together to tell me how to push my telescope. So I get fast feedback from the IMU, but the IMU is constantly corrected by the plate solve whenever possible. So this is the system. And the problem that comes up here is IMUs, at least the ones I am using, are not really sensitive to small movements and jerky movements. So once my offset is starting to look like this, 0.0 degrees in altitude, 0.2 degrees in azimuth, the IMU is sort of useless. So at this point, I want to present the user with something very intuitive on how to do this last mile. And the way I do that is that I have a display right next to my telescope here, right next to my eyepiece. And with this display, I present the user with a correctly oriented PAWS image. PAWS is Palomar Optical Sky Survey. It's digital, is DSS. You might know it as DSS. It's basically there. Okay, you can think of it as this. There exists a software and a database that I can query. Hey, give me a photograph of the sky around this area and deck, and it'll do it, right? With north orientation guaranteed. So basically, what I do is in that display that's right next to my eyepiece is present a picture of what I'm expected to see in the eyepiece from the digitized sky survey, correctly oriented. And that way the user can do the last mile in the eyepiece. So if I'm, let's say 0.2 degrees away, that movement is much easily done with feedback at the eyepiece. So what I show the user is something like this, that says, hey, your object is at 6 o'clock, 1 field of view away. So you just move the telescope. This is very intuitive. You just move the telescope such that you bring the object from 6 o'clock to the center. And yeah, so the last mile is really straightforward, like this. And so that's the entire system. So it's plate solving to calibrate the IMUs for fast feedback to get to the last mile, and the last mile is an eyepiece with a reference image guiding you in exactly which direction and where the object is, right? So in practice, this system can such a system can be built, in my opinion. I think all that is left is engineering work. And so this is sort of my North Star system. And it'll have this sort of user installation where the user just removes their existing finder scope, puts in this electronic finder scope, which is fully integrated. It has its own computer running plate solving like a Raspberry Pi or whatever. And they mount an HDMI tablet or a display next to the eyepiece and connect wirelessly to the system. And in the ideal user experience, the combination of fast and slow loops are so seamless that iterations are not needed. Right now, I actually need to iterate about 4 or 5 times to get to the object. So I'll move my telescope and then I'll let go of it, wait for a plate solve, and the plate solve recalibrates my IMU. So my offset might be looking like 0.5 degrees, and then it'll say, hey, it's not 0.5 degrees, it's actually 1 degree because the IMU is drifted. And so I have to do about 4 or 5 iterations to narrow down on the object. I'm not doing any star hopping. I'm just letting the plate solving recalibrate my IMU. So hopefully we can engineer a system where this is not necessary, and the fast and slow loops calibrate so quickly that you don't need to like stop, wait, and iterate. And ideally, I think this is achievable. You want the object within 2 arc minutes of where the plate solving claims that it is. And I think we can also have a situation where we can develop a pointing model, and that pointing model has much lesser of a task than it would if you were using encoders. Because with encoders, things like how level your scope is, how well the axis is aligned with the actual axis of the telescope, these things matter, how solid your mount is. Whereas here, in this system, all that matters is thermal drift and the flexure difference between the 2 optic axes, the one of the finder scope and of the telescope. So the pointing model here, assuming that thermal drift can be solved, only has to learn flexure. And I think that's so I believe that you might be able to increase the model of this, the accuracy of this pointing model with just a few data points. Okay, so here's where I'm at. I'm going to show you a demo of my system that I recorded the last time I set up my scope. Unfortunately, the punchline of this demo is not great, and that was the only opportunity I had to record it. but I'll show it to you anyway. Um, Hi. When I roll this clip, if you can hear the audio and see the video, would you just give me a thumbs up? Let's see if I can full screen it. And yeah, there might be that flicker again, so I can't do much about it.
This is
Yeah, we hear it.
it's essentially a 70mm Orion finders
Pretty quiet though.
connected to a ZWO camera. We don't.
I don't know how to fix that.
That's good. That's good.
Is it okay?
It was
Yeah,
better.
in your sharing, if you select optimize for sharing audio through Zoom,
Oh,
you
okay.
can actually do that when you share. At the bottom, there should be an option for you to select that, and then what it'll do is it'll pipe your system's audio into the feed into Zoom.
Oh, I see. So it doesn't do that otherwise. Okay. So let's try this. Is this better?
This is the electronic finder scope.
Much better.
It's
Okay,
essentially a 70mm Orion finders multi-use finder scope connected to a ZWO camera. We don't really need a fancy camera like a ZWO. We could probably get away with a faster and smaller finder scope or lens and a simpler camera than something that's used for real astrophotography. Strapped to this finder scope is an Arduino, which is a microprocessor, and it connected to the Arduino is a motion sensor, the IMU shield for the Arduino. We have this mess of wires going to my laptop because my prototype involving the Raspberry Pi, which is a single board computer, did not quite work out on the field and needs some re-engineering. But in principle, all of these wires could be eliminated except a few going to the secondary cage, which I'll talk about. And you could mount a board computer right here. And of course, you will need some way to power it, so there'll be some power supply wires. And now let's take a look at the secondary cage of my telescope. Here's a 7-inch LCD display that has been mounted. Currently it is showing nothing, but it's red filtered, and it has a touch panel overlay on top of the red filter, so you can still use it like it's a touch screen. And an HDMI cable runs down to my computer from here. This is to show a reference image, pause image for what I'm seeing in the eyepiece. And now I actually have here a trackpad, and that trackpad can be eliminated. It's there because I have a driver issue with multi-touch for the panel that's pasted on top of this touchscreen. If we used an AMOLED display, which doesn't have a backlight, like Ed Allen does on his telescope, then we should be able to just use the native touchscreen of the display rather than have all of these complicated workarounds to red filter a regular touchscreen, LCD touchscreen. My telescope rides on an equatorial platform, which is seen here as a black item, and that makes the mathematics harder. But unlike with DSCs, you do not need to reperform a 2-star alignment every time you reset your platform, because the finder scope is attached to the telescope. So any offset outside of that system doesn't affect the performance of the system. So the platform only complicates the math. So I have currently set up the software, connected it to the camera and other things, and centered Alpha Persei in the telescope. So I'm going to, once I have centered it, I'm just going to double check that it's centered, and then I come back and hit align, and I'm going to click this yes. Once I confirm that it's centered, I'm just going to push this dialog onto the other screen so that I can see it up there. So now that I've centered Alpha Persei, I'm going to go ahead and ask it to align. So it's performing the 1-star alignment right now, and we can come back to my computer screen. Basically it's plate solving right now as we speak. Okay, so now that the alignment is complete, I'm going to enable the plate solve loop that I have described. It's going to keep taking exposures and keep solving them. I've also set it up to target M77 as the object, and it's resolved with my planetarium and set as the target. Now I'm going to go to my telescope. So you see, it's not yet giving me guiding instructions. That label that just says guide has no instructions on how to push my telescope as yet, and that's because the IMU calibration, remember, requires 2 data points. So I need to generate the second one by going to my telescope and moving it in altitude by about 10 degrees. This is so that it can fix the magnetic magnetometer, or so that it can fix north without relying on the magnetometer. So now that it's done that, you see it just takes another solve, and now I have guiding instructions. So all I needed to do to get that second calibration point was to move my telescope. So now, and here's the part that needs a lot of improvement, but it's possible to improve it. I'm going to use the IMUs to push my telescope. So I just brought my telescope into range. So as you see, as I move my telescope, these numbers are changing. So I just need to follow the instructions and get them to as close to 0, 0 as possible. So now with a few iterations, I've gotten close, and I then can do the last mile in the eyepiece. Let me pick up my flashlight. So as you can see in this display, I'm not far. The object is just below in my eyepiece field of view at like 6 o'clock. And remember, this is oriented correctly, and that circle actually does represent the FOV of my current eyepiece, which is a 6mm eyepiece on this telescope. So I'm just going to bring it in from 6 o'clock, and there's the object. It's right there. And now let me center it to show you that the solving is sensitive to that kind of difference. So I have now centered it in my eyepiece, and once the solver hits again, it should show it pretty close to center. Yeah, I think that's the amount of error I have right now, what you're seeing.
So I wish that I would have hit much closer to center, but I think I know what's going on. I changed the sling that holds my primary mirror to what's called a glatter sling. And I think there's a problem where my mirror and collimation sort of shift every time I move the telescope around because it's on a platform. So anyway, so basically I think I have a problem where my mirror is physically moving as I jerk the telescope, and it doesn't go back to center. So actually I'm losing collimation. This is because I have a sling mount. And I think that's the primary source of that error. But the error that you saw at the end, so what you should have seen if we had perfect positioning is that object M77 should have been right in the center of that display, in the center of that circle. But the error that instead it was at the edge of the circle. So the error that's there was 6 arcminutes. And I am complaining vehemently about a 6 arcminute error that is not due to flexure. So, so I am very dissatisfied until I get it down to 2 arcminutes. So that's where I'm at. Anyway, so So what I'd like to try next, and I'm looking for suggestions and contributions, and this entire system is sort of non-commercial. I don't plan to make anything out of it. I have to go through some bureaucracy with my employer to release the software as open source. So I can't share the code or the software yet, but I'm happy to share all the other ideas like, hardware, mathematics. Yeah, just ask for it. So the things that I'd like to try is transition to a shorter focal length. So I'm currently solving with a 270 millimeter focal length. And the problem is that my limiting factor that is giving me that final error is flexure and imperfections in my mount, or imperfections in the way my telescope preserves alignment, and not not the pixel size of my image, right? Not the resolution of my imaging. So if I go to a shorter focal length, I might be able to get away without tracking because the star smudging is not going to be detected by the algorithm. And I might be able to get shorter exposure since brighter stars are likely available in this larger FOV that I will get. And in fact, one of my friends who I've been talking to, Harshad, who is the author of this app called Sky, he reports 5 arcminutes accuracy with just a phone camera, right? So it's pretty impressive, just with a phone camera to be able to get that kind of accuracy. And he's worked on improving it even more. And he's trying to build a product that'll work with his app. So the other thing I'd like to try is transition to a lighter and cheaper camera, because right now my finderscope system, let me just pull it out so I'm not talking in the air. So this is my finderscope. It's a typical imaging rig attached to a finderscope. This thing
you're still sharing your screen if you want.
Oh, right. So maybe I'll just pause share for a moment. How does it work? Yeah. Can you see me now? Okay, yeah, so this thing has a lot of flexure because this body of the camera and all of that is really heavy. So that's something I want to move away from so that there's not as much flexure. And another great thing is you probably use ZW, some of you probably use ZW ASI 290 cameras for imaging. The same sensor that's in those, probably a lower quality run or whatever, or lower quality electronics and stuff, the same IMX 290 or 291 sensors that are in those cameras are available for $35 on Alibaba or whatever. And there's a set of people who run this global Meteor network who are already using it to catch meteors at 25 frames per second. So they're just buying these $35 cameras and creating all sky cameras that are catching meteors for them. And I was talking to Peter, I forget his last name. I was talking to a person named Peter from Albuquerque at Okie Star Party, which is where all of this video was shot. And he was telling me that, yeah, they're seeing pretty good star density with just this camera. So I'm very curious, and I bought the board. I just haven't had the time to go and put it in and try it out. The other thing I want to do is transition to a single board computer. So I already have my full plate solving stack running on RPi 4B+, and it takes marginally longer to plate solve. And unfortunately, my field test failed. And I think it's the power supply stability issue. So I need to stabilize the power supply. And I also would like to eliminate as many wires as possible. So that's where I am, what I'd like to try next. And that's pretty much the end of my talk. I'm open for questions, comments. I have a few extra slides with pictures in case somebody wants to see. Maybe I'll stop on this picture of the software UI. This is the prototype software UI I built in Python to orchestrate this entire process. Yeah, that's my talk.
All right, thank you very much. Well, questions, anybody?
I'm just curious about the algorithms. Akarsh, when you do the fusion of the information from the fast loop with the one from the slow loop, are you using by chance Kalman filters?
No, that is a very interesting question. I should be using Kalman filters, but I'm not. The reason is I haven't figured out how to use Kalman filters. So I don't have background in that domain of sort of probabilistic modeling or whatever you would call it. I'd like to acquire background in it. One of the challenges is I built this entire system using quaternions, and if I were to write down how to do this sort of maximum likelihood estimate in terms of quaternions, the math looked really complicated, right? Because the surface, if you like, on which I have to take derivatives is, this is getting into mathematical details that might not be relevant, but it's the quaternions are equivalent to points on the surface of a three-dimensional sphere. So the normal sphere that we know has a two-dimensional surface, but just imagine one extra dimension. So it's a three-dimensional sphere. The possibilities of rotations, which are quaternions, lie on that space. And I don't know how to formulate this Kalman filter mathematics in that domain. And whatever literature I could find on it was too hard for me to understand. So right now, I'm just recalibrating with no memory, right? Every time I get a point where I can figure the orientation, I use that. Every time I get a point where I can also figure the magnetic north, which is I need a big shift in altitude for that. I just use it. So they're point estimates and they don't have any memory. And that's something I'd love to fix.
I was wondering, one of my previous hobby before astronomy was RC models. And I remember when people started flying drones with Arduino, many people use the Kalman filtering using an IMU to get the raw data for the essentially rotations and angles.
Right.
And from that, they do some form of dead reckoning to figure out where is the next position where your airplane will be. But given that drifts over time and is fast but not precise, every once in a while they correct it with GPS data, which is essentially the same thing that you're doing. But you're not, of course, based on GPS, but based on plate solving. So maybe you can find some pre-cooked code in the ArduPilot community.
That would be extremely helpful. So thanks for that. I think it is, I want to say it might be, I don't know, honestly. So I know that GPS plus accelerometers is a very common steady problem. It's in fact like I was watching some video on Kalman filters and that was the example they gave. Yep. The problem with astronomy, I guess, is you don't have this sort of three-dimensional situation. Everything lies on the surface, if you like, of the celestial sphere, right? So you have a very different geometry.
Look up particle filters, Akarsh.
Particle filters?
Yeah, it's a sort of non-parametric relative where anyway, just look it up. It's probably not appropriate for this.
I'm sure to note that down because
video.
That's extremely useful. So particle filters. So yeah, I don't have any background in this domain, and that's one of the things I would really like to fix is to use filters rather than point estimates.
I was going to ask you about the display. Is it possible to do a heads up, like a display inside the eyepiece?
Yes, we've thought about that. Me and a friend brainstormed about it. I think it's extremely challenging. So for example, you could in principle place something behind your secondary mirror that would illuminate, but then you would have to scale it based on what eyepiece you're using. It would be really nice to have a heads-up display, of course, but the second thing is, you should have the ability to interchange eyepieces so that whatever you have, whatever display logic you have should be robust to that, which I think is extremely challenging. or you have to somehow place it inside every IPs, which gets sort of expensive and impractical. So that's sort of why I think that's way beyond my engineering abilities right now as somebody who's prototyping.
Yeah.
The
How
other
about
thing is-
voice? How about audio, like wearing an ear, a Bluetooth headset and the thing somehow pinging you without being too annoying? Because I would imagine that, don't you want to keep your eyes in the telescope while you're doing all this and while you're moving it around? And it seems to me like if you're moving away and looking at your display and then coming back, you're being.
That's a good point. Yeah, I haven't thought about that. That could be useful. Yeah, I never thought about audio because, yeah, that could be useful. So right now I haven't had any issues using the display because it's like I mentioned in that video that I shot. I put an actual plexiglass red filter on it. Anything that, in my experience, unless the display is very good at doing a zero intensity black, right? If you don't put a plexiglass filter on the display and you're just using red gelatin, or you're trying to use the display's internal settings, or like digitally say that, display only red pixels. My experience is, unless the display is very good, it's going to still leak a lot of white light that will hamper your adaptation. And so I went through this extra length to put this plexiglass screen, and now it doesn't bother my adaptation to look at that. So I haven't had so much of a problem with it, but you're right. It's much nicer if I could just keep my eye on the IPs all through. Yeah, I'll think about that.
Hey, Akarsh, this is Pavan.
Yeah.
So I have the night vision eyepiece. So I think that's probably much more relevant to the question, right? Because there is an electronic viewfinder there. And I'm wondering if that can be plate solved, but I know it has its own circuitry and stuff. So
yeah, perhaps, because then you might have control over that phosphor screen and be able to decide what you display there. Yeah, maybe you could integrate a heads-up display into night vision eyepieces.
I do not know if night vision eyepieces can transfer that image out to a computer though.
Oh, I see what you're saying. So you're saying plate solve in the actual eyepiece without having to deal with the finder scope. Yeah, perhaps.
Why can't you use a bino viewer? So that way you can split the image, put the other one on the other side, and then sort of kind of plate solve that way.
Yeah, the problem is whatever I described earlier, right? The stability of the tracking and of this mount, it's so shaky that you will have very smudged stars. That's the problem number one. Problem number two, unless the camera is extremely sensitive, which night vision devices are, so that I think is a possibility. The second problem though is that solving tiny fields takes longer, so you have to make sure that it's not a blind solve, and even then you're just searching through more fields, deeper star indices. One of the advantages that I have is, I don't know how much you've tinkered with plate solving, but there are these huge index files that are based off various catalogs, right? One of the advantages that I have with the wide field finder scope plate solving is I can load the entire index and hold it in memory. So it's in my cache. The very second time I hit plate solving, it's no longer reading from the SSD. It's just reading from memory. So that improves the speed of my solving. The problem with the large star indices is that you'll have to do something very clever. You'll have to use your IMU's position to figure out what is the rough RA index, prefetch the indices so that they are in memory corresponding to that RA index, and then run the solve so that it's more efficient. So I just feel that has its own share of complications. Of course, this finder scope method also has its own share of complications, which is flexure and really and thermal drift. And I have really no proper way of modeling those. But I think night vision eyepiece is an interesting idea. If you have a camera that you can hook into your eyepiece or into your focuser that has enough of a sensitivity that you can run very short exposure, so none of this vibration matters. And then you design the software such that it doesn't do a blind solve, but it narrows the search space as well as possible. I think then it might be possible. So that's a good idea. Yeah. I think you need both. You need a bino viewer with night vision eyepieces on one side, so you can still have interchangeable eyepieces on the other side.
Exactly. That's really what I was trying to get at, right? So that way you have the camera mounted on one, and then you can change your eyepieces on the other. And
Yeah, it's a very interesting idea. Yeah.
All right, any more questions? I'm happy to entertain them. Okay, well, if not, Akarsh, thank you so much.
Sure, you're welcome.
And, it was a great
Thanks for
talk.
giving me the platform.
Well, it was wonderful to hear. It's impressive work, and thanks a lot. And
Thank you.
hopefully, yeah, everyone say thanks. And we'll see folks in December. Again, like I said last time, we're looking for speakers. If you have something to contribute, please volunteer. Francesco, did you have something to say? No. Okay. Okay. Well, thanks very much. And that's the end of our November meeting. And we'll see you all later. Goodbye.
Thank you very much.
Thank you.
Happy Thanksgiving, guys.
Happy Thanksgiving.